now, Miss Area, are you right?
Yes.
Okay. So, you know the gene, human gene, Gene, genome, human genome.
Genome.
Yeah, you must be heard of this before, genome. And DNA, yeah, these keywords, chromosome. Okay?
Is that how you spell it?
Yes. So, our human, you know how different people look different, yeah? Different hair color, different eyes, right? These controls by gene, right? And then we human have 23 pairs of chromosome, okay? 23 pairs of chromosome. Each chromosome has hundreds of genes, right? Yeah, hundreds of gene pairs, okay? So 23 pairs. And one of them controls the sex, the gender, right? For example, the boys are XY, the girls are XX, okay? The girls, okay? The boy, okay? So mommy and daddy, if mommy and daddy going to have one more kid, yeah, one more baby. So what's the probability of this kid being a boy, and what's the probability of that being a girl? Remember, how do we calculate this out? We take
50-50.
Yeah, how do we take one of these and we combine it with one of these. Okay, so what's the probability of XX? Look, if we take
XX and XY.
yeah, look at X. I pick this X, XX, yeah. Pick this Y, YX, right? Yeah, YX. Okay, so
There
they look.
isn't any XY.
Yeah, YX is the same. Okay, XY. Okay, so look at these two. There are two. 2 out of 4 boys, 2 out of 4 girls. Okay, so boy, girls, 50-50. Yeah, 50-50. Yeah, 23 chromosomes. One of them is controllers. Yeah, the sex, the gender. Okay, so as I said, each chromosome has 1,000, many human genes. Yeah, human genes, and the genes are. There are 4 types of, the DNA. Yeah, DNA is the two stranded. So you will have these the pairs, gene pairs. Yeah, gene pairs. So it's like a two stranded.
But there's only 8 pairs.
Yeah, I'm just drawing a few. Okay, I'm drawing a few. So these. They only have 4 types of gene, which is A, C, G, T. Okay, you don't need to worry about how you pronounce. This is just different symbol to represent. There are only 4 types of genes, and A always pair with T, C always pair with Z. Okay, so here if it is A,
I just wanna see what it stands for.
oh, it's a very very long the biology terms which you probably don't remember.
I just want to hear it.
Yeah, we can Google it later, okay?
It's gonna be blah blah.
Yeah, it may be more than 10 letters, okay? Look, if this is A, what's this going to be?
T.
Okay, if this is G, what's this be?
C.
Okay, exactly. So what? So look, it comes with pairs. That means that the DNA, this DNA, can be easily repairing itself, right? Right? If one of them is broken, right? This is broken, right? Your human body knows because this is G, so he knows this is C. Get it? So that's why your human body is repairing itself, right? It knows how to repair DNA, right? Yeah? And it can replica easily, right? With these. So it's very, secure way of chain, right? It's match, yeah? Okay? Okay, so yeah, I'm not an expert on this biology. Okay, just these things, just the basic. Okay. So now, coming back to today's problem, we have a gene group. Okay. So look, A. If I have this one, let's consider only one side of it. Yeah. Yeah. If this is A, C, T. Okay. If there are 4, right? If let's consider 4 pairs. Okay. A. I write the ACCT, so automatically know the pair, yeah? TGGA, right? Yeah, automatically. So let's say this. Let's just use the left hand, okay? DNA comes two pairs. You know, you might heard of other words which is called RNA. Yeah? RNA is only one singular. Okay? So let's say ACCT. And two genes, if they belong to the same group, if they only differs one gene, for example, ACCT and let's say AGCT, they belong to the same group. Why is that? Because they only differ one. Yeah, make sense? Yeah. Okay. So now, if I give you a list of the gene, yeah, gene mutation group. Okay. Let's say gene mutation because they only differ by one, and we say they belong to the same gene mutation. Because look, if you change these to here, there will be a mutation. That belongs to the same mutation group. Because it has one step, one difference. Make sense? Now, okay, so I give you this ACCT, AGCT, and I have given you TTCC. How many groups? How many gene mutation group are there? How many? Two, right? Two, yeah. Because these two belong to the same. These two is different, so there are two groups. Make sense? Okay, so today's task is this. Given a list of genes with the same length, we want to find out how many groups are there, the mutation group. Yeah? Make sense? Yeah? Any idea how can we do it? I mean, this problem may be a bit, think about it. Yeah, think about it. So look, if we consider these as a node, the graph, yeah, graph is the collection of vertices and edges. Right? So if I can have this ACCT as a node, as a vertex, and AGCT as a vertex. So, and here is another one. So I can consider each gene is a vertex. Right? So is there an edge between these two? Yeah? Yeah? Because they belong to the same group, right? Yeah? So I can add an edge, right? Right? And then there is no edge, right? So the problem becomes what? We want to find the number of components, the groups for the graph. Make sense? Yeah? So our task is to find, given this graph, yeah, we given this a list of genes, we know this graph, we can represent the genes in this kind of graph. And the edges connected to different genes who belong to same mutation group, right? For example, I can have another one which is what? CGCT, right? Because these and these only differs by the first one, right? Make sense? Yeah? So we can look at the whiteboard and then say, okay, there are two components, right? Yeah? Make sense? Yeah? Okay, so now we are asking computer to do it. Remember, what kind of algorithm can we use to traverse the graph? We want to find the number of components.
Buffer search.
Yeah, buffer search and depth search, yeah. Depth search, we can do this depth search easily today, okay? Or we can talk about buffer search the other day. And also we can use the union find, disjoint graph, right? There are disjoint set, remember? Disjoint set, yeah? We could talk about that someday. Disjoint set, union find. So look, for disjoint set, we have this vertex, we have this vertex, we find out they belong to the same vertex group, so we merge these two, right? And then later, we find out this and this belongs to the same vertex group, same mutation group, we merge it. And then we find out, and then later we find out, we can just say, okay, how many groups, how many connected components are there? And then you can easily tell us that there are two. Okay, so for the depth search, we try here. We start with any node. If it's not being connected, right? We start from this one, and then we try to visit and mark all the vertex, yeah, right? And then we mark it and we increment the answer, which is 1, right? Look, here, I'm here. Answer equals 1, right? And I mark the connected. Okay, this is being marked. I skip. This is being marked. I skip. And here, this is not being marked, not being visited. Right? And there might be some other group here, which is what? TTCA. Okay? Right? And then now I increment the counter, which is 2, and I mark it. You see? That's depth first search, yeah? Make sense? Okay? You right? Okay. Okay, so let's do this depth first search today, and we talk about breadth first search, disjunctive some other day, okay? Because I think depth first search is most easy to understand today. So define, we want to find the number of groups, yeah? Let's say find number of groups. And we're given this gene. Yeah, gene. So in order look for the graph depth first search, we need a kind of data structure. Remember the nodes we have visited, right? What is it called? The thing. What are the data structure? What is the data structure we use to keep tracking of the nodes we have visited? So we can remember. Yeah, notebook set. Okay. So we can say scene equals set. Set will be nothing at the beginning, and then let's say have a G, which is the gene. Let's say we put it in a set, so we can easily find if a gene is in the input by using this hash set lookup, which is O1 constant, right? And now we can do this. Define depth first search, and then we starting with A, right? We are now here. So and now here I want to say answer equals 0, okay? And then I can say for I in gene, well, if I not in scene, and I need to do answer plus equals 1, and then depth first search I, okay, and then I return answer. Okay, so look here, if I write it here, then there will be a standard template for performing the depth first search on the graph, right? On the graph, look, I going through this gene. Yeah, I know, I haven't finished yet. For genes you can consider it as a vertex, right? It's the same thing here as the vertex, right? I'm going through the vertex. I check if this vertex is not being visited, then I increment the one answer and depth first search from this, right? Depth first search. Okay, so now after this return answer, that will be the number of the connected groups. Now depth first search A, and then first thing I want to add it to the scene, right? Scene dot add. Okay, I have visited this A, right? And I need to, okay, so now I have this gene, CCAA. What's its neighbor? What's it connect to? Remember, we talk about the mutation group, right? So it only differs by 1 character, right? So it could be what? C could be the 1 character will be what? It could be, this could be A, this could be G, right? This could be T, right? So then its neighbor is connecting the vertex. It could be ACAA, GCAA, TCAA, okay? Or it could be different by here. It could be another one. CAC, the second character, yeah? CAAA, CGAA, yeah? You see? CTAA, am I right? Yeah? Because I say, look, this one connects to which one? It only differs by 1 character, yeah? So we can brute forcing this because like we only have 4 kinds of possibility for each gene, right? So we can brute force all its possible neighbors and then check if it's in the original gene. So let's say for I in range length A, and then for X in, okay, so there are 4 possibilities, A, T, C, G. So what's current? C, the neighbor will be what? Neighbor will be A up to I, right? plus x plus a I plus 1. Okay, so this is the neighbor. Look, I try I in range this. I try each position. Instead of using the original character, I use the previous one. I use the next, and then for this one, I brute force all 4 possibilities. Yeah? Are you okay, Eric?
Mhm.
What happened to your eyes?
Okay.
Okay, yeah? And then look, if n not in scene, right? If this node is not being visited, and also we need to do this n, also this n in already original, then we do this one, depth first search, n, right? Yeah, this is the depth first search. You see? Okay. I say it again, okay? We go through the gene equals the vertex, okay? Gene equals vertex. Gene is the vertex. We go through the vertex. If we haven't visited this vertex, we increment the answer, right? We have one more component, and we try to mark the neighbors. We try to visit it I, depth search from I, from current node. So for the first thing, we visit this vertex, we have to put it in the visit table, right? Scene in the notebook. So next time we know, right? So next time if it's visited, it doesn't go in again, right? And then we go through like each character. We try to replace it with all 4 possibilities, right? And n is the neighbor, right? And neighbor is not in scene, it's not being visited, and also it's already in original G, n in G, right? Look, you can say n in genes, but if you want to find the item in a list, it takes O(n) time, right? So that's why I converted the list into the set. So that will give me O1. Finding a number in the set, time complexity?
One.
O1. Finding a number in the list, time complexity? It's right above it. Sorry?
N.
Yeah, that's why we convert it to set. So the hash table, so it will provide us O1, okay? Yeah? So let's therefore search. We can do this another way, which is what? So instead of scene, we can do what? We can have a left, right? So we want to find out the number of, so this thing is allow us to keep tracking of the nodes we have visited. And how about, let's say we have the vertex, and every time we visited the vertex, we just remove it, right? Remove it. So let's say we can have this. Left equals set gene, okay? Genes. And then we don't need this scene. And then depth search, then instead of scene.a, we can do what? We can say left.remove a. Remove a. Yeah? And this is the same. Then we can say if n not in left, instead of long EC, we can combine these two into one, which is if n not in if n in left, right? Okay, this is the opposite. Okay. So look, with the scene, it's we checking if a node, if it's visited. If not, then we do the depth search. With the left is that if the node is still in the left, then we do the depth search. And then here again, if I not in scene, we change it. If I in left, okay? And we'll do the depth search. Make sense, Eric? Any questions? I mean, this is a little bit too much for you to digest, right? Eric? Kind of. But you understand the principle, right? How do we do it? Okay, so how do we do it? Look, I have ACCT, I have GCCT, I have TCAA, I have another one, CCAA. So how many groups are there?
They are.
So this is the genes, the vertex. And then I need to find out which two are belong to the same group by differing one. These two at one edge?
Yeah, one.
And these two? Yeah, TCAA.
Oh, yeah.
Yeah. Right, okay. So how many groups are there?
2.
Yeah, easy. So how do we do it? We start with any vertex. If it's not invisited, we increment the answer equals 1, yeah? Plus 1 answer. And then what do? we mark it, visited.
Visited.
If it's visited, we will skip, and then we go to here. We increment the counter, and then we do the depth search. Yeah? Visited. Simple as that. This is the template for the depth search. Look, yeah, forget about the genes, whatever, right? The genes, the vertex. Now, the difficulty here is that the graph, it doesn't give you the graph directly, right? Eric, the difficulty is that it doesn't give you the edge directly. You need to figure out the edge, right? And how do we figure out the edges? Here, we try to go through each letter and then try to replace it with 4 possibilities. Yeah? Yeah, if it's in the gene, then we add it, there's an edge. So what do we do if there's an edge? What do we do if there's an edge?
We count as a group.
And then? Depth search it. Yeah? So it's easy? Huh? Makes sense?
Mm-hmm.
Okay, that's it for today. Good job. Bye bye.
Bye.
Bye bye.